Hey guys, so we'll analyze this problem today. So we'll study an inclined plane, and the problem we'll analyze is this guy, right? He's on a horizontal surface right now, and you increase the angle, right? And at some angle, right? So friction is keeping him intact, right? But at some point, gravity, so gravity and friction are fighting with each other, right? Now, at some angle, we know that gravity wins and this guy will start sliding down, right? So we'll just um, look at that point at which this guy is at the verge of sliding. In other words, we need this angle over here, this angle theta, at which this guy will just start sliding. He doesn't start sliding, he's just about to slide, okay? So let's draw this. So here's the scenario, right? There's that guy. I'll show him as a box, easier to draw, right? So he's at the verge of sliding. This is the weight, straight down, normal force is over here. And friction, since he's just about to slide, right? The static friction force is maximum. Remember, static friction force is a variable force, okay? General static friction force is less than equal to mu s times the normal force, and its maximum value is equal to mu s times n, right? So as this guy is, as I'm increasing the angle, right, the static frictional force is increasing, and at this angle, he's just about to slide. It's maximum. It cannot be more than that. And if gravity increases, the component of gravity increases beyond that, then the guy will start sliding. Okay. So this is that limiting angle at which this guy will start sliding. Okay. Beyond which this guy will start sliding. So let's look at the components. So I've discussed this before, that if this angle is theta, this angle is also theta. Okay, so if you want to review it, you can go back to the video of frictionless inclined plane. Okay, so this component again is W cosine theta. This one, W cosine theta, and this guy is W sine theta. Okay, so you can show the W sine theta over here also. So W sine theta. Okay, so we now know the components of the forces. So normal force goes up, and this is again our axis, right? And W cosine theta goes down, W cosine theta goes down, W sine theta is towards the right, and static frictional force is up the inclined plane towards the left. Okay, so let's write Newton's second law now for the two directions. Okay, so F, the sum of forces in the x direction is equal to 0. The object is static. Okay, so the net force is 0 in both the directions. Okay, Fy equals 0. So in the x direction we have W sine theta minus Fs max is equal to 0, and in the y direction we have n minus W cosine theta equal 0. So this gives us Fs max equals W sine theta, and this gives us n equals W cosine theta, right? Now Fs max, as you can see, is Fs max is mu s times n, right? So you get mu s times the normal force equals W sine theta. Now you can plug this in. You can call, let's say, you can call this equation 1, this equation 2. You can say that you're plug 2 in 1. You're plugging 2 in 1. Okay. So you get mu s W cosine theta equals W sine theta. So this is our result, that this angle mu s is this coefficient of static friction is equal to mu s tangent theta. Okay, so, or you can, if you know, let's say, the coefficient of static friction, we can figure, if we know the angle theta, is we're increasing the angle, you can measure the angle at which the guy is just start sliding, right? So that's going to be theta, and then you can get the coefficient of static friction between the two surfaces. Okay. Now the beautiful thing is that it's independent of the mass. So in this case, this guy was a Lego fireman. No matter if it's a car or a truck, you can. It's independent of the mass of the object, which is very interesting, right? So that's your angle. You can also write this as theta equals tangent inverse. Okay, same thing. Okay, so this was it for this problem. If you have any questions, post them in the comments. If you like the video, press like and please subscribe. Thank you for watching.